But by the way, if you have any questions, so don't hesitate to ask. The topic of the lecture is properties of the Ornstein-Uhlenbeck semigroup. We'll see a few strong and important properties of this semigroup, especially hypercontractivity. Let me remind you what we did last time. So for a centered Gaussian measure gamma for now on n-dimensional space, the Ornstein-Uhlenbeck semigroup acts on each space LP by the following expression. So this is the integral of f e minus tx plus square root 1 minus e minus 2ty, and we integrate over y. We proved that it is indeed a semigroup in the sense that it sends a function from LP into a function from LP. Moreover, it is contractive. It has the semigroup property, and it is strongly continuous in the sense that the norm of action of the semigroup minus f in LP converges to 0 when t converges to 0. And this is true for all f from LP. When p is equal to 2, we also have that the semigroup is symmetric. And non-negative. So here the inner product is taken in L2. As any strongly continuous contractive semigroup, it has a generator. And today we will look at the generator of the semigroup on L2. On L2 with respect to the standard Gaussian measure. So it is denoted by L. It is called the Ornstein-Uhlenbeck operator, and it is defined as a limit when t converges to 0, ttf minus f divided by t. Such limit may not exist for all f, so it is defined on a domain. I will write it just as follows, that limit exists. In fact, we had a description of the domain. Okay, let me write that f is in L2 gamma n. We had the following description of the domain. So the domain of L consists of functions from L2 for which the sum of k squared norm ikf squared is finite. And here ik is the orthogonal projection onto the span of Hermite polynomials of degree k. I will denote them as hj1 times hjn. This means that hj1 is taken from x1 and so on. Hjn is taken from xn, and we take the product. And j1, jn are such that their sum is equal to k. So this is the description of the domain. And also we proved that on this domain, the operator acts as multiplication by minus k. Okay, but the question remains: what is this actually? What is the domain? What functions are in this domain? Because the description in terms of convergence of the series, it is nice, but it is not very instructive. So which functions belong to the domain of the Ornstein-Uhlenbeck operator? And we will describe these functions using the notion of the Sobolev space. First, let me give some notations. So HL is the space of L linear forms on Rn. So this is a mapping of Rn L times into R. I'm sorry. Forms are linear in each argument, and the usual inner product is defined as follows. So we take all possible vectors from standard basis in Rn. In all possible combinations, we substitute them into the forms and multiply. So this is the so-called Hilbert-Schmidt inner product. All right, and if we have a function which is L times differentiable, then its Lth derivative can be viewed as an element of HL. It's like the L's time derivative in directions y1, yl, and it is actually equal to such sum. In particular, if we consider the norm of dl f of x squared, it will be, I mean this Hilbert-Schmidt norm, it will be the sum over all y1, yl from 1 to n, partial derivative with respect to coordinates I1, IL, f of x squared. Yeah, actually, I will use a bit different representation since we can permute these indices, and this will not affect the value of the derivative, we can write this sum as follows: the sum of m1 plus mn is equal to L factorial over m1 factorial mn factorial, and here the partial derivative with respect to x1 m1 times, partial derivative with respect to xn mn times f of x squared. So we split all possible combinations y1, yl into combinations where we have a fixed number of ones, which is m1, a fixed number of twos, which is m2, and so on. Okay. And now let us define what is the Sobolev space. The Sobolev space with respect to the standard Gaussian measure is the completion of the space of infinitely differentiable functions with compact support with respect to the following norm. So R defines the number of the derivatives that we include into this sum, and P is the P corresponds to the space LP. So explicitly, we have the following expression. So we integrate f to the power p, then we add integral of the derivative of f to the power p, and so on until the derivative of order r. You know that the infinitely differentiable functions with compact support, they are dense in LP. When we define Sobolev spaces, we define them as spaces of functions that can be approximated by infinitely differentiable functions in LP norm, but also in such a way that the derivatives of these functions, they have also limits. And these limits can be understood as generalized derivatives of functions from this space. So now I will explain it in more detail. So assume that we have a function from the Sobolev space. Then it can be approximated by infinitely differentiable functions with compact support in LP in such a way that all partial derivatives of these functions fk, they have also some limits in LP. And then we can define the partial derivative of f as the limit in LP of corresponding partial derivatives of fk. And here we have to ask a question. We can take some other sequence that approximates f. Will we get the same limits for this approximating sequence? In other words, we need to define, we need to prove that such a definition of the derivative of f is correct. So this means that assume we have a sequence of infinitely differentiable functions that converge to zero. And their partial derivatives, they have some limits in LP. What we must check is that all these limits, they are also zero. One way to do this is to compute the Fourier transform of G I1, IL with respect to the standard Gaussian measure. So let Pn be the density of standard Gaussian measure. And okay, let's say that this is the integral of a Fourier transform. G is a limit of partial derivatives of Fk. And now what is natural to do is to integrate by parts L times and say that, okay, then Fk, since Fk converges to zero, so we will get, this is a limit, we will get a zero in the limit. But this integration by parts must be justified because we integrate over all Rn. This is the first, and the second, Fk, let's say, may converge to zero in L1. So then the question, why integrals converge? Because after integration by parts, Fk will be multiplied by some unbounded function. So to do this, we use inductive argument. So we will prove that all functions g are equal to zero by induction on L. When L is equal to zero, we already know this because by assumption Fk converges to zero in LP. Now let's take some compactly supported infinitely differentiable function zeta and look at the derivative of zeta times Fk. If we differentiate the product L times, we will get a sum of products of derivatives of such a kind. So here, zeta is differentiated by some amount of indices, and Fk is differentiated by some another amount of indices that form a partition of I1, IL. Okay, and now our induction assumption works. So if m is greater or equal to zero, then here we have less than L indices. So in the limit, it will give zero in LP, and this is a bounded function. Now, it follows that the derivative I1 IL of the product zeta fk converges to zeta times g I1 IL. And now all integrations by parts are valid because zeta has a compact support. So we write g, we write zeta times g as the limit of zeta times the partial derivatives of fk, and the L times integrate by parts. And now what we get the product of fk with a bounded function because it has multiple zeta. So integrals will converge to 0, and we make a conclusion that g times zeta is equal to 0 almost surely. But zeta is arbitrary function, infinitely differentiable with compact support. This means that zeta times g equals to, it means that g is equal to 0 almost surely. Okay, so we defined Sobolev spaces, and for each function f from the Sobolev space, we defined a derivative of order up to r. So you may ask why to complicate things. It turns out that Sobolev spaces, they contain not only differentiable functions. For example, as an exercise, you can check that a function maximum of x and 0 belongs to the Sobolev space W21 with respect to the standard Gaussian measure on the real line. And also you can find what will be the derivative of this function and check if this function belongs to W22. Meaning, can we find the second derivative of this function? When p is equal to 2, we can give necessary and sufficient condition when a function belongs to the Sobolev space W2R. Square integrable function belongs to W2R if and only if the following series converges. This is sum k to the power r times L2 norm of kth projection of f squared. Okay. First, assume that the sum converges, and we know that in L2, f is represented as a sum. So for finite n, consider the sum from 0 to n of projections of f. Explicitly, this is the sum k from 0 to n. Then we take the sum over all Hermite polynomials of degree k, the inner product of f and Hermite polynomial, and times this Hermite polynomial. Now let's prove that Um, let's prove that all the derivatives of Fn have limits in L2. So consider the derivative of f of order L. We m1 times differentiate in x1, and so on, mn times differentiate in xn. I recall that the derivative of kth Hermite polynomial is equal to root of k times hk minus 1. This means that if we differentiate hj1 m1 times, its order will be lowered by m1, and we will get the multiple root of j1 factorial over j minus 1, j1 minus 1 factorial, and so on for each Hermite polynomial. Of course, here must be an assumption that m1 less or equal to j1, but I don't write it here. So if m1 is bigger than j1, then the corresponding summand will be 0. So we get such an expression for the derivative of Fn. Then if we take the norm squared, we will get the sum over k, then sum j1 plus jn is equal to k. So instead of root, we will get just this ratio, and times f hj1 hjn squared. In fact, this ratio is j1, j1 minus 1, and so on, j1 minus m1 plus 1, then j2, j2 minus 1, and so on. It can be estimated just as the product of j1 to the power m1, jn to the power mn. And this whole thing is just less or equal to the sum of k to the power l, because j1 plus jn is equal to k. So we get an estimate which shows that all derivatives of Fn they have some limits in L2. Okay. Now it is not hard to see that every polynomial can be approximated by infinitely differentiable functions with compact support with all derivatives up to order, say, R. This can be done by multiplying Fn by some infinitely differentiable function of the form x over R and take R to infinity. So this is very similar to how we showed the correctness of the definition, that this will converge to Fn. Psi has to be taken in such a form. 1, 0, 0. And also all the derivatives of this function, they converge to the corresponding derivatives of Fn. This means that there exists a sequence of infinitely differentiable functions with compact support that converge to F, and all derivatives up to order R also have limits in L2. This means that the function F belongs to the Sobolev space. Okay. Now, to prove the converse, first consider the case when F is itself infinitely differentiable and it has a compact support. We expand F into its orthogonal, into the sum of orthogonal projections. This series converges in L2, but we will now check that it actually converges in the Sobolev space. To do this, we find the expansion for all derivatives of F. Consider the inner product of, let's say, dx1f with some Hermite polynomial. Now, since F has compact support, we can integrate by parts. And when we differentiate hk1 x1, also we have the density of the standard Gaussian measure. So when we differentiate this, we get hk1 prime minus x1 hk1. Okay, but last time we proved that actually hk prime coincides with x hkx minus root k plus 1 hk plus 1. So we obtain root k1 plus 1 times inner product of f and h k1 plus 1 until hkn. Okay, if we do this many times, we get the following relation. So the derivative of f, its inner product with a Hermite polynomial reduces to the following. It's the product of f with a Hermite polynomial in which for each component the index increases. The order of the polynomial increases by the number how many times we differentiate in this component. And we also get such multiple. So in the expansion, this will be multiplied by hk1, hkn. Now note that when we multiply this by the root of this ratio, we exactly get the derivative of order m1 of k1 plus m1, and so on, derivative of order mn of h kn plus mn. It means that in the expansion, this term will coincide with this term, and so on. All right. As a consequence, consider the projection of this function onto the space of Hermite polynomials of order k minus m. This is the sum over all g1 plus gn equals k minus m of inner products times Hermite polynomials, but we already computed this. It is equal to such inner product of f, but with other Hermite polynomials, and multiplied by the derivatives of other Hermite polynomials. And now let's change the order of summation. So instead of g1, jn, let's sum in g1 plus m1, jn plus mn. Then we will get the sum over all j1, jn that give sum k. However, here we also need to write that j1 is greater or equal to m1 and so on. But in fact, it is not needed, because if j1 is less than m1, then m1's derivative of hj1 is equal to 0. So we get that the projection of this derivative of f onto the space of Hermite polynomials of order k minus 1 coincides with the corresponding derivative of the projection of f onto the space of Hermite polynomials of order k. And now we can get the expansion. The last equality is true because if k is less than m, then the derivative of order m of ikf will be 0. So now what we see that Fn converges to f in L2. All derivatives of Fn converge to corresponding derivatives of f in L2. This means that this expansion holds in the Sobolev space. In particular, polynomials are dense. And also note that Hermite polynomials are orthogonal in the Sobolev space. Because when we take two different Hermite polynomials, I mean of different order, they are orthogonal in L2. When we differentiate them in same variables, we will also get Hermite polynomials of different order. So they will be also orthogonal. Or maybe one of them will be 0. This means that actually Hermite polynomials they form orthogonal bases in the Sobolev space. It is not orthonormal basis, but it is an orthogonal basis. This means that for the function from the Sobolev space, such series must converge. And now we estimate this norm. So it is enough only to consider the squared norm of the highest derivative of order R. Since the norm of each Hermite polynomial is 1, and when we differentiate, we get a factor of the root. So the square norm of Hermite polynomial hj1 m1 is equals to the product j1, j1 minus 1, and so on, j1 minus m1 plus 1. Okay, so to estimate it, consider k large enough. I mean, let's k will be greater than 2nr. And assume that the sum of j1 plus jn is equal to k. Then the maximal summand is at least k over n. And consider indices where in ith position we have r and other positions are 0. Then we get such an estimate. And this will be greater or equal than k over n minus r plus 1 to the power r. But our choice of k implies that this is greater or equal to k over 2n to the power r. Okay, so we have this estimate that for large enough k, this expression simply less or equal than the norm of f2r squared. And then it is finite. Okay, so we get a necessary and sufficient condition when the function belongs to the Sobolev space of the type 2R. Now recall that the domain of L consists of functions in L2 such that the sum k squared norm ik f squared is finite. But this is exactly the condition for the function to belong to the Sobolev space W22. Okay, so we get another description of the domain of the Ornstein-Uhlenbeck operator. The following is the so-called integration by parts rule. So here g is the function from Sobolev space W21, f is the function from the Sobolev space W22, then the integral of the product of gradients of g and f is equal to minus integral of g times LF. So this justifies the possibility to in some sense take the derivative from g to f, even though this is not a usual derivative. Well, it can be shown relatively simple because we already know quite a lot about Sobolev spaces. Let's just take expansions of f and g, and as we saw, the gradient of Fn converges to the gradient of f, the gradient of Gn converges to the gradient of g in L2, and also Lfn converges to Lf in L2. So it is enough to check this formula for polynomials. Then it is enough to check it for Hermite polynomials. And finally, observe that when g and f are Hermite polynomials of different order, then left side and right side are equal to 0. So they can be taken of the same order. Let's say hj1, hjn. Let k be the sum of j. If we take the summand that corresponds to derivative in I, then the integral will be equal to ji, because the norm of Hermite polynomial is 1, and the squared norm of the derivative of Hermite polynomial of order ji is ji. Okay, and in the sum we will get k. But on the space of Hermite polynomials of order k, operator L is just multiplication by minus k. So we will also get k. Okay. Another property is the representation of Ornstein-Uhlenbeck operator. It is equal to the Laplacian operator of f minus x times the gradient of f. This is the sum from 1 to n, partial derivative in I f of x, minus sum I from 1 to n, xi, partial derivative of f of x. Again, this is enough to check for Hermite polynomials. So hk double prime of x minus x hk prime of x. This is equal to x hk of x. minus x minus k hk of x. Okay. And maybe I want, yeah, so again, we can get the following formula that the gradient of the Ornstein-Uhlenbeck semigroup of F is multiplication by E minus T of the gradient of F. So again, it is checked for Hermite polynomials. So now let's turn to the following property, the logarithmic Sobolev inequality. It states that for every function from the Sobolev space W to 1 that is non-negative, the following inequality holds. So here on the left is the integral of f squared log f. It's less or equal than the integral of the norm of the gradient squared plus 1/2 the product of the integral of f squared times the logarithm of the product of the integral of f squared. The main idea behind this inequality is that f squared can be viewed as T0 of f squared. Log of f can be viewed as, let's say, 1/2 log of T0 of f squared, d gamma. So this is the left side. And also on infinity, Ornstein-Uhlenbeck semigroup converges to the integral. Okay, so this is like T infinity of f squared, and this is log of T infinity of f squared. And now if we put this product into the left side, we get like the same function, the difference of the same function at 0 and at infinity. Then we can write it as the integral of the derivative in t from 0 to infinity, and use the properties of the Ornstein-Uhlenbeck semigroup. So by usual approximation arguments, it is enough to consider the case when function is infinitely differentiable, bounded with all derivatives, and separated from 0. If we replace f squared with phi, we get here phi, here log phi, here 1/2, okay, here phi, and since f is a root of phi, the gradient of f is 1/2 root of phi, gradient of phi, and squared we have 1/4 gradient of phi squared over phi. So we obtain equivalent inequality in the following form. And now use this argument with the representation of this difference as the value of some function at 0 minus the value at infinity. So this will be the minus integral from 0 to infinity. The derivative of such integral. We can compute this derivative explicitly. When we differentiate Ornstein-Uhlenbeck semigroup, we get Ornstein-Uhlenbeck operator times tt phi, okay, times log. When we differentiate log of ttf, we get 1 over tt phi times the derivative of tt phi. But recall that tt phi is symmetric in L2, so it preserves integrals. Then the second summand is 0. Okay. Now we can use integration by parts, and instead of L, here we will get the inner product of the gradient of tt phi times the gradient of log of tt phi. And finally, when we compute the gradient of the logarithm of tt phi, we get this thing. Okay. Now, the Ornstein-Uhlenbeck semigroup is defined as a certain integral of partial I phi e minus t of x plus 1 minus phi, and here d gamma y. So let's multiply this by root of phi and divide by root of phi d gamma, and apply Cauchy inequality. So the square of this function will be less than the product of tt phi and tt times the of the ratio, the derivative of phi squared over phi. And also recall that e minus dt, let me check, Yeah, so t of partial I phi equals to t minus t partial of tt phi. So here in the left side, we get the sum I from 1 to n, the integral of partial I tt phi squared over tt phi d gamma. Okay, and this ratio will be less or equal to e minus 2t dt dt phi squared over phi. After integration in gamma, this is a constant. Okay, so in our previous estimate, now what remains is to integrate over t, and we will get exactly the factor 1/2. Okay, so this is the logarithmic Sobolev inequality, and it has a number of consequences. So one of them is hypercontractivity. So here t is positive and fixed, p is greater than 1, and q is greater than 1 and less than 1 plus p minus 1 e to the power 2t. It turns out that if the function f belongs to LP, then the action of Ornstein-Uhlenbeck semigroup on this function sends it into LQ. And note that Q can be bigger than T. Moreover, the norm in the space LQ with a bigger Q is less than the norm of F in LP. So this is what is called the hypercontractivity. It can be deduced from logarithmic Sobolev inequality. So what must be proved is that the integral of TTF to the power Q of t is this expression, d gamma to the power 1 over Q of t is less or equal to the norm of f in LP. Again, we assume that f is infinitely differentiable and separated from 0. So denote this as the function g of t. Then the right side is exactly g of 0. So what must be proved? It is enough to prove that g is a decreasing function. So here you can see how the derivative of g looks like. So it is enough to prove that this thing is non-negative, non-positive. Okay, also q prime of t equals to 2 q of t minus 2. So it is bigger than 0. We can divide by q and q prime and multiply by q and get an equivalent inequality of this form. So now the derivative of f has this form, which may look complicated a little bit. But if we substitute, we get an equivalent inequality like this. So q prime cancels. We get q over q prime here. And this is minus f log f over q. And it looks much like the logarithmic Sobolev inequality. Consider the function g, it will be tt of f, and denote qt to be r. Then we apply logarithmic Sobolev inequality to the function g r over 2. Then in that inequality, we have integral of the function squared, so it will be integral of g to the power r log g d gamma minus it must be 1/2, I think. Yeah. No, it's not 1/2. It's here must be log g to the power r over 2, so we will get a factor r over 2 minus 1/2. And then after dividing by r over 2, we will get this inequality, which is after integration by parts, it is actually the one we need. Okay. So one consequence of this hypercontractivity is that the projection operator, it acts, since this is a projection, it acts from L2 to L2. Actually, it acts from L2 to any LP. This is not as surprising because the value of this projection will be always a polynomial. However, the norm of the projection in LP can be estimated by the norm in L2. and estimation is as follows. To show this, let's take Q equals to 1 plus we can write P as 1 plus 2 minus 1 to the power let's write P as 1 plus exponent nt, exponent 2t. Yeah, for some t bigger than 0, the Ornstein-Uhlenbeck semigroup acts on the space of Hermite polynomials of order n as multiplication by e minus nt. As e minus nt I n f. And now we can take the norm in LP and use the hypercontractivity. Then this is less or equal than the norm of INF squared. And this is less or equal than norm of F squared. So it remains to multiply by this exponent and write it as follows. Okay, and the last thing is the so-called Poincare inequality for functions from the Sobolev space W to 1. The following inequality holds. The left side is like the variance of the function with respect to the measure gamma. And on the right side, the integral of the gradient squared. This is easily follows from integration by parts, because on the left side we have the sum IKF squared from 1 to infinity, because we subtract I0. And by integration by parts, on the left side we have minus FLF. But L acts as the multiplication by minus k on the space of Hermite polynomials of order k. So the inequality now becomes obvious. Okay, so that's all for today. Thank you for the attention. Maybe you have some questions. Okay, so if there are no questions, then see you on Friday.
Thank you. See you next.